Quite know what to expect when Mike Randall shows up with the wonders of physics. Today we're going to measure the speed of light through chocolate. I can't wait to see what...
Well, actually, with chocolate. Light doesn't go through chocolate very well.
With chocolate, okay.
So kids, here's your big advantage, okay? Make sure your parents aren't listening, but here's your excuse to get your parents to buy you chocolate. Tell them it's for a science experiment, okay? So what we're going to do is it involves, is a piece of chocolate. By the way, any food that melts will work for this, okay? It could be cheese, mini marshmallows, whatever. But, you know, if you have your druthers, might as well do chocolate. Right. Yeah. You'll need a ruler, you'll need a calculator, and you'll need a microwave oven. First thing you want to do is disable the turntable. You don't want to have the turntable going, so in my case, I could take this little plastic thing out.
Okay.
You do not, that's very important, I'll explain why later. You put this in here, and depending on the strength of your microwave oven, you let it go for anywhere between, 10 and 30 seconds, okay?
Okay.
Just depends on the strength of the microwave. I'd start it off at 10 seconds and then check it.
What are we looking for?
What you're looking for is little melted spots. We're going to let this one go. This isn't a very strong microwave, so we're going to let it go for a little bit. But because the table isn't rotating, you'll get hot spots. You know, I grew up with old-fashioned microwaves, and it's like before there were turntables, you had to go in every so often to turn it because microwaves don't heat evenly. And that's the reason for that is physics. In a microwave, there we go. So now we see...
Oh, there are hot spots.
We've got some melted spots on this chocolate. I don't know if you can see that. Yeah, you can see that very well. So we're going to set that aside for now, but here's what's going on. Microwaves, a microwave is a type of electromagnetic radiation, which sounds impressive, but light is a version of that, radio waves, all of that. Being a wave, there's certain things that a wave will do, particularly in a confined space. So the waves have a wavelength.
Here, can
so that's the difference. That's the distance between one high point on the wave and the next. And they have a certain frequency. How many waves will go past a point in a certain amount of time? And if you have them in a confined space, these waves will bounce back and forth and create what's called a standing wave. And anybody who's ever taken a piece of string and tied it to something like a doorknob and then shake it, you'll see points where the rope will be going up and down very quickly, and other places where it's not going at all. The places where it's not moving at all, those are called nodes. And the places where you have the most movement are called antinodes. Antinodes are the places where you get the most heating. So that's why microwaves heat unevenly. But we can take advantage of that. If we measure the distance between the center of these two melted points, and granted, these are kind of big melted points. So you're just going to...
Can I hold it up like that? Yeah. Before it slides off? Yeah, okay.
You're going to try and you do this in centimeters.
Through the middle of the hot spot? So
trying to pick out the middle of each hot spot. In this case, I'd say maybe a little bit more than 6 centimeters, okay? That is the distance between one peak and the next, okay? Or actually, one of these peaks and the next, the antinodes. If we double that distance, that gives us wavelength. Why do we care? If we know the wavelength and we know the frequency, by the way, the frequency, look in the back of your microwave. It's printed right there. It tells us a special number. In this case, it's 2,450 megahertz, or 2,450 times a million cycles per second. You take that number, you punch that into your calculator, you punch in the number you just found out, which is, let's say it's 6 centimeters. You double that to 12. You multiply those two numbers together, it will give you the speed of light in centimeters per second. Okay? Now, speed of light is such a fundamental value, and it's very hard to measure very accurately. But with something as simple as this, you can get to within maybe 2, 3, if you're careful, within 2 or 3% of the actual value.
So can you give us a ballpark of what it should be, or you want it to be a surprise?
Well, it's going to depend kind of on your microwave oven. They should all have pretty much the same frequency, but look on the back, because that's the number that'll vary it. It should be right around 6 centimeters, typically, maybe a little bit bigger. I could tell you the exact number, but then that's giving too much away. I'll let you look that one up online. By the way, the instructions on how to do this, along with a whole bunch of other fun stuff, is on our website. If you go to wonders.physics.wisc.edu and click on the Kids tab, there's all kinds of fun activities for you kids to do this summer, including this one. And it'll give you some more detailed instructions just like this.
And for parents, too, if they need a little assistance, it is step-by-step instructions, exactly what you need and how to proceed through it. A wonderful way to incorporate a little science.
This should be done with parental supervision, because this chocolate does get hot, and then you're running a microwave, but it's not a terribly big deal.
And let it cool before you eat it.
Yes, yes. And make sure you have plenty of graham crackers and marshmallows on standby.
All right. So now we've measured the speed of light using a bar of chocolate.
Yes, we have.
Who'd have thought? Mike Randall, thank you so much for coming in. And once again, get your fix on science and maybe pique the kids' interest throughout this summer. Well, coming up, we're going to take a look at your Weather Authority forecast. We'll be right back.